So this is going forward with the cost function idea. We had already discussed this, but this is a cost function, okay? And it is the total cost to produce items, okay? So if I produce X items, if I produce one item up here, C of 1, and I plug 1 in for X, it would cost me $2,002.001. If I wanted to produce 2 items, it would cost me, and so forth, all right? Now this is, and again, people a lot of times say, it can't possibly cost that much to build 1 than 2. Yeah, remember, $2,600 is like the fixed operating cost of the business. It's the heat, it's the management, it's the mortar down the building. But what we did at the end of class last time was we started a chart. We had X as the parts produced, cost of parts. So we had 1,000 was 5,600, 2,000 was 10,600, 3,000 was 17,600. And what the catch is, this 1,000 parts here costs five grand. This 1,000 parts costs $7 grand. Because again, when we optimize a manufacturing facility, you put too many monkeys on the football. And eventually you have to go to old machines or other machines that cost more money to produce things. This is a real world cost thing. Now, if you're the customer, you don't care about my problems with overhead. What do you guys want to know? How much each part costs. So how do I find the cost of each part? Average, total cost divided by quantity. Does everybody agree that would be written like this? And I picked some easy numbers. So 5,600 divided by 1,000 is $5.60 each. Okay? The next one is $5.30 each. All right? And the next one, dun, 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 is $5.87 each. And it's somewhere in between there. Now someone, again, if you want to stay at 5:30 and use the same machine, maybe you can't make the delivery date. There's lots of real-world situations. But we want to optimize. We know somewhere between most likely 2,000 and 3,000, there is a minimum for price. If we want to find the minimum, what do we want? The derivative. But I really don't want to do this. I want to do this as a function. Well, the book, this is really hard, especially with my poor handwriting. This is the total cost over the quantity, right? Well, the book says, hey, that's capital C of X, total cost. So little c of X is equal to the cost for one part. Well, that's equivalent to this. This is the cost for one part. This is the number of parts. This is the total cost, okay? So I think I can find this function, though, pretty easily, all right? Because little c of X is dividing this thing by what? X. And can X be 0? No, we're not going to make 0 parts. Okay? So I'm going to divide it, and I'm going to do it in one step. 2,600 over X plus 2 plus 0.001X. That is the cost per part. If I make 1,000 parts, this will be the cost. If I put 1,000 in here, I'll get 560. That's the function that generates that. Well, what do I want to do? I want to optimize the cost per one part. So what do I have to do to this cost per part? Take the derivative. All right? I want to optimize it. And I'm not going to spend a whole lot of time here doing this. If I do this, I can get little c prime of X equals what? Negative 2,600 X to negative 2 plus 0.0001. Right? And if I want to optimize, I want to minimize my cost here, I can set this whole derivative equal to 0. All right? And if I do this, I can say, okay, this here equals 0, right? So I can say 0.001 equals 2,600 over X squared. All right? And I can do the math here. And the book does it a little differently. So So 2600, right, divided by 0.001 to like 2.6 million. I got to take that to the 0.5. And I get x equals 1612.4516. Now here's the thing. We got to use our noggin for something besides something to keep hair on, okay? Can I have 0.4516? No. I have to make a decision here. And I'm going to say, hey, this is optimized. I'm going to round. 1,612 items is the minimum. Now, if I want to know the cost for this, what do I have to do? I'm going to do the intervals. Yeah, I got to plug it back into this function right here. Right? And that's what I'm going to do. And if I plug that back in, and I get C of 1612, and I'm going to cheat and use my nose, boom, it is $5.22. So if you can optimize for a client, the best price you can give them is $5.22 per, and it has to be in that type of quantity. Anything less is going to cost more, and here's the irony: anything more will cost more. All right, that is hard to sell. If you are actually on the other side making parts, you have to set this price high enough that if someone orders 2,000 parts, you can still make money. Because the expectation of customers, I'll tell you this right now, is the more they order, the better price they expect. So usually we play with delivery time. But yeah, I can deliver 3,000 parts, but instead of being 2 weeks, it'll take me 4 weeks. And I do 1612 twice. You guys follow me? But again, it's always constrained on time and things like this. Yeah. Well, it depends on what you're making. I've had items that I've sold for pennies. And I've also had items I've sold for huge amounts of money for ideas. Well, again, when you create the equation, you do this by mapping your business. And you tell Excel, hey, give me the best fit polynomial for this. You can tell it to do order 3, you can tell it to do order 4, you can tell it to do order 5. You have to decide how far to go and where does it make sense. And that's just trial and error. And is your business a square, a cube? You know, does it have an effect on the cost? I'll tell you what, going beyond a square for me never made much sense, but I'm not an expert at cost. This is economics, guys. Remember, my background is really mechanical engineering, with just enough math to be in here torturing you guys. All right? Whatever the state of Wisconsin minimized for math requirements, how I got in here. This is economics. All right? And this is how we minimize, maximize stuff for that.